it is on. Come on, let's start. Thank you.
Okay. You guys can hear me perfectly? Okay. So before we start, how many of you are software engineers or you code regularly? Can a quick show of hands? Alright, so many of you. How many of you work in AI and ML? Okay, good. So I'll tell you a little bit before we start. So this is going to be a very introductory session about the field of computer vision. The idea is to get you to understand how computers deal with visual data, how they read it, how they process it, so that once you go through this session, you will be able to understand the other cool stuff that other speakers talk about. So when Sir talked about when Sir talked about pose estimation. So how do you actually recognize where that particular point is on the body where you have to draw that pose marker, right? So how do all those things happen? It is like, so this is basically the ABCD of computer vision, and once you learn the ABCD, you can learn sentences, so on and so forth. So forget about computers. The most powerful vision system on the planet is the human vision system, right? And let's test that a little bit. What is this? Can anyone answer? Oh, sorry. I hope you guys can see it. Yeah. What is this? It's a cat, right? What is this? Blood cat, right? And what is this? It's a yes, outline. Right, thank you. It's an outline cat. Okay. So we looked at three images. What did we learn about ourselves? So humans can recognize and identify visual information no matter what. I can show you an image of cat under any condition, lighting, blur, a different type of cat, and you will be able to determine that it's a cat, right? So one clap for appreciation for the human visual system. Come on. Okay, let's go a little further. What is this? Good. What is this? A man. Okay. And who is this? Spider-Man. Good. So, what did we do? We combined visual information from two different sources and we determined meaning from it. Now, of course, like combining Spider-Man to make Spider-Man does not make that much sense. But let me give you another example. You're driving on the road, you want to make a right turn. You want to look in your rear view mirror to see if someone is coming from the backside. And you're also going to look at your left so that no one is cutting through the line. So you're combining two different scenes, processing them in your head, and then making the decision whether you should turn right or not. Another clap of appreciation for the human vision system. Okay. So now that begs the question, why are we so good at looking at things and making sense? Now, if you remember from school, we were told that we have 5 basic senses, fundamental senses: vision, smell, touch, taste. I may be wrong, but yeah, I'm hearing as well. Okay. So it's one of the most fundamental systems that the human body functions on. The other thing is that human vision is also capable of adapting to different conditions of lighting, blur, occlusions. Now I'm standing here, right? And there's a desk in front of me. But you can tell that I have legs, right? Because I'm standing. You can't see them, but you know that I have legs, right? So it's an adaptive vision system. So other thing is that not just the sensing part of it, but also the ability of human brain to look at images and determine meaning from them, right? So combining all these together, you develop a very good vision system, and you also are blessed with genetics of your ancestors and also other beings on this planet. So it's a system that has developed over centuries and years and also your own lifetime. Now, we talked a lot about humans, we are all amazing, right? Now, let's get a computer to do the same thing. What is this? What is on the screen? It's a number 3, right? This is how you look at a 3, right? Squiggly line. This is what a computer looks at when it looks at a 3. Does that make any sense to any one of you? It does, right? Does not to me, because I have to explain this, so it can't make sense right away. Okay, so when a computer looks at an image, what it is looking at essentially is a grid of numbers, right? And you will see that these numbers are 0, most of them are 0. Then you have some numbers like 74, 254, 99, something, right? And if you look closely in this image, wherever we had the squiggly line of 3, those are the same places where we see those numbers. Okay? Now, why is this? Computer as a system inherently only understands number because it's a digital system. So ones and zeros. So everything you feed into a computer is fed as a number. Whether it's text, whether it's audio, whether it's images, any kind of data has to have a number representation so that a computer can understand it, right? So now how do you represent images to a computer? So the very first representation of an image to a computer would be a grayscale image. This is the most basic, the most simplest way to represent an image. A grayscale image is basically a black and white image. Now how is it represented? You have a 2D array. For non-tech people, it's a 2D grid. And each value in that grid would be from 0 to 255. Now 0 means black, that is no value there, and 255 means completely white. And everything from black to white would be grey in the range of 0 to 255. Also, as you go from 0 to 255, what it also represents is intensity. So let's say behind this wall, it's completely dark. Behind the projector, I hope you can see that through the mirror you can see that it's completely dark. As I start moving forward, it gets brighter and brighter. So that is 0, all the way up till this line, it would be 255 here. So it represents the intensity. But black and white is very old school, so we also have RGB, right? So RGB is the most common representation, so it's a colored images. Now for RGB, you have a 3D array. So basically, you have 3 arrays, one representing the intensity of the red color, the other representing the intensity of the green color, and the third one representing the intensity of the blue color, right? And each of these intensities is individually represented as a 2D array. Then there are also other kind of images which are multispectral and hyperspectral images. A 3D image conveys color as an information in each of its channel, I would say. A multispectral image can convey more than just color. So let's say someone talk about thermal images. So you can have RGB and then you can have one channel which can talk about the infrared coming out of a particular point. You can also have the same thing talking about depth, right? So those are multispectral images. Now for this use case, we would stick to RGB. We would not go for color. So now we understood what a computer looks at, right, in terms of what an image is to a computer. The next question is how to make a computer see what we want it to see. So let's start with a very simple example. If you remember, how many of you have taught kids, like taught? Right? You would have tried. So when you teach little kids to identify things, you teach them, okay, tell me what color is this. Then when you want them to explain their images, you start with shapes, like what shape this is, right? So we'll teach our computer like it's a kid. So we'll start with a very simple image. Now this is a square. Please tell me why this is a square. Okay, I hear 4 sides and same length. 90-degree angles, good. So the key point here is that it has 4 sides, right? That means it has 2 horizontal edges and 2 vertical edges. Also the other point is that all of them are of the same size. I skipped out on that part, so I apologize for that. But the main point here is that the reason why you know this is a square is because it has 2 vertical edges and 2 horizontal edges. emphasis on the word edge. This will be useful. Now, to detect square, I need two vertical edges, I need two horizontal edges. So the first thing I need to detect is an edge, right? So how do we determine edge? Now, edges tend to have a property that wherever there's an edge in an image, there's a sharp gradient, right? Now, what is a sharp gradient? You look at this projector screen, right? It has a black boundary, and the screen itself is white. When you go from that black boundary to the white, there's a line, there's a very thin line, right? That's your gradient. So a gradient just means a location where there's a change. In our image of square, you have the white background, right? And then when you move to the orange square, you are basically changing intensity from white to orange. Okay, this is clear? So this is basically the logic behind an edge. Wherever there is a gradient, I will have an edge. So now, to determine a square, I want to find out edges, and in order to find out edges, I need to look for gradients. So that means I need to look for something in my image. So now we'll see how to look for things in an image. Before we get into looking at things, I want to introduce a concept of filters. I remember that in the past few meetups, past couple of meetups, we have been talking about filters. Those who have been here, they will know. And I think in the last one was about Kalman filters. So we are not going to discuss anything complex. We are going to talk about filters from a very basic perspective. How many of you have seen those color films that you put on top of a lamp and it will turn red or green or blue? You have those small plastic sheets, right? That is essentially a filter. Let's look at an example here. Again, we have Spider-Man, and then I superimpose a green filter on top of it. Now, what a filter is essentially doing is any light that is passing through the filter will get, let's say, multiplied by the intensity of that filter. And it will depend on what that particular pixel is. So if you look, the maximum effect of this green filter is where the eyes are present. Because the eyes are white in nature, and you can see that it is green, turns them green. So I would like to talk a little about filters now by showing some examples. Alright, so this is the code that I wrote. Now, you need to understand filters. So what a filter essentially does, maybe go to the slide first. Okay, no. Okay, so what a color filter is doing? Let's say you have a grayscale image and you have a color filter. Now remember that the color filter will be 3D, right? Because to represent color, you need 3 channels. So the color filter would be 3D. You will multiply your grayscale image by the color filter, and then we get a colored image. In this scenario, I have used an image of that is grayscale. I have used the red color filter, and the output will be red. I'll show you in code how that happens. So, okay. So this is our input image. This is a simple black and white square. The white boundaries represent the square. And let's focus on this part. So here I'm creating a filter. Do you guys need a very detailed walkthrough of code, or can I go through the lines quickly? Okay. It's visible in the back, right? You guys can see the lines of code on the projector, or shall I zoom in a little more? Okay. So, in the first line, what I am doing is that I am initializing a simple color filter. So, I'm basically creating 3 arrays, one for red, one for green, one for blue. And initially, I am setting them all to be 0 in intensity. So you basically have three arrays of black, black, and black. In the next part, I'm initializing a red filter. So it is copied from that base filter, but if you would see, here I have seen 0 equals 255. What is this? It's basically, you have three RGB channels, right? So red, green, and blue. So it's essentially a three-dimensional array. So you have one two-dimensional array. So the first two indices represent the two dimensions, right? And then the third index here represents the channel. So 0 would be red, 1 would be green, and 2 would be blue. So the red filter would basically mean that the first channel is 255, everything else remains black. Similarly, green filter, the second channel would be 255 and everything else will remain black. And blue filter would be third channel black and everything 255. Now, we can also have a colored filter that is apart from RG and B. So I have a sandy filter. Now, what the sandy filter is that you give some intensity to red, you give some intensity to green, and you give some intensity to blue. And then you basically, so this is a function that takes your input image, applies a filter on it, and gives the output. And this is just code for plotting. So yeah. Now, this is my base image. When I apply the red filter on it, it gives me a square with a red color. So think of it in the same way. You have a torch that is giving white light. You put a red paper on it, and you're getting red image. Similarly for green, blue, and then the sandy filter. Now to talk a little about the math of this, or to explain this in detail, we'll come back to the slides. So let's simplify this. Let's say we have a checkered box image, right? Where the diagonals are all black and everything that is not diagonal is white. And then you have your filter. It's a red filter, and the image is a 3x3 image, right? This is basic math, right? I hope everyone gets it. Okay. So so input image is 3x3 in size. It's only one channel. You have filter that is completely red, and green and blue are obviously set to 0. So again, the filter is also of the same size, 3x3. It just has 3 channels. So when you want your output, what you will do is that for each of the filter channel, you will do an element-wise multiplication between the image and the filter. So element-wise multiplication is basically the value at 0, 0, the input will get multiplied by the value at 0, 0 of the filter, and that will be your output. How many of you understood this? Okay, cool. So where there was white, when you apply filter, it will turn red. Where there was 0, that means black, it stays black. Okay, so this is the fundamental concept of filters. Now you might be thinking that I started by talking about detecting edges. So why are we talking about filters here? Now it turns out to be that filters are the most basic instruments of image processing. Whenever you want to deal with images, you have your raw image, you want to do any kind of processing on top of it, you will have to use a filter, right? Filters also create the basis of a very fundamental operation which is called convolution, and we'll talk about what convolution is. Okay, so let's start by talking about convolution. So up until now we have seen image multiplied by a filter, it gives you the filtered image, right? Now there are two properties. First of all, when you multiply it by a filter, you're basically doing an element-wise multiplication. So it's straightforward multiplication of one image by another. Also, the input size and the output size and the filter size are all the same. Convolution gets a little tricky. So to explain convolution, I would like to take this example. Let's say you have an image of people. I give you a magnifying glass and I ask you to find specific people in it. If I'm looking at this image from far, I may not be able to tell it. With a magnifying glass, I can take it and I can run it over the image. And once I get the zoomed in view of the people that I want to look at, I can say that, okay, this is the man I was looking for. And then in that image, I can place a marker and mark that person. That is also what the image conveys. Okay? So this is the fundamental concept of convolution, is that I have an image and I want to look at specific parts of that image, right? Now, how does this work? Consider an input image that is 0, 1, 2, 3, 4, 5, 6, 7, 8, and you have a kernel. What's a kernel? Kernel is basically a filter, so it's another name of a filter. You can call it a filter, you can call it a kernel. Just as I'm taking my magnifying glass and I'm running it through the image, in the same way, I will take this kernel and I will start sliding it over the image. However, the operation now is not just element-wise multiplication. Wherever I'm placing the kernel, in the first case, let's say we start by placing it on the top left corner. So the first two elements of the first row and the first two elements of the second row would be under the filter. They get multiplied. So 0 times 0, 1 times 1, 3 times 2, 4 times 3. Right? And then you sum these values. So 0 plus 1 plus 6 plus 12 gives you 19. Right? Then I slide my filter. So now it comes to 1, 2, 4, 5. Right? I have slided it. Then 1 times 0, 2 times 1, 4 times 2, 5 times 3. Sum that, you get 25. Okay? If I have to visualize it, you can look at this GIF. So what is happening is that you have taken your filter and you are sliding it over this image, and each time it slides, it does an element-wise multiplication and sum, and you get this final output. Okay? This operation is clear to everybody? Yes? Quick show of hands. Does anyone feel sleepy? No? Good. Okay. So now you might be thinking that ये सब चीजें तो सही है, but how do I detect edges, right? That is the main point. So let's start. Now I don't just want to dive into edge detection, rather I want to model it as a convolutionally solvable problem. So how do we do that? Consider I have an image of a box and I want to detect the vertical edges in the box, right? So the question I want to ask is, what is going to be that filter that will slide over that image and tell me these edges, right? That is the question. So again, I have an image, I want to determine what will be that filter that will tell me what the edges are. Okay. So for that, some people have already done the hard work for us. So we have a filter that's called a pre-bit filter. Now it's essentially a 3 by 3 matrix. So the first matrix is -1, -1, 0, 1, 1, 1. So that is used for determining vertical edges, right? So all the vertical lines in the image would be determined by the vertical filter. When you transpose it, you get the horizontal filter for determining edges, right? Now, how does this work? I have again taken a sample image. So you have basically a 4 by 4 matrix. The left half is completely dark and the right half is completely white. So that means at the boundary of the left and the right half, there should be an edge. So I take my filter, I impose it on the top left side, and I do the convolution operation. So you can see -1 times 0, -1 times 0, 0 times 0. And then where the value is 1, it gets multiplied by 1. And then I sum these together. When I sum these values, I get a positive number, that is 3. Everyone is following the math for this one? Okay. So you get a positive value, 3. That means you have found the edge. Now, this also works in the case where there is no edge. Let's say if all of this entire matrix was all ones and I placed the filter on it. So you would get -1 times that first row would be -1 multiplied by 1, second row would be 0 multiplied by 1, and the third row would be 1 multiplied by 1. Right? So you get -1 plus 0 plus 1. What is that? 0. So that means it will not find an edge. Okay? Works like magic. So now let's look at a little bit of a demo of this as well. Okay. So again, we start with an image of a square. So I've loaded the image and I'm using the OpenCV library. And then these here are my filters. So I am designing a vertical filter here, which is simply a 3D array. And as I explained previously, -1, 0, and 1 vertically stacked. And then you take the transpose of that and you have a horizontal filter. Now, to determine the vertical edges, you basically do this convolution operation on your input image and your vertical filter, and then there is some post processing. Similarly, if you want to get the horizontal edges, you do convolution of your input image along with the horizontal filter. When we plot it, we'll see these three images. So the leftmost is your input image. The one in the middle detects all the vertical edges, and the one at the end detects all the horizontal edges. Now here's a catch. I have written leading vertical edges. What does this mean? If you look at this image of the square, it is a thick square, right? That means it will have an edge where you start sort of enter that frame. Then you will also have another edge when you exit the boundary and go towards the middle of the square, right? However, currently these filters are only determining the leading edges and not the trailing edges. This has to do with the structure of the filter itself. If you look at this filter, when it goes from left to right, what it tries to do is, it will look at these gradient changes in that direction only. So when there is a change in left to right direction, that is when it will detect it. If it doesn't happen that way, it will ignore it. Similarly, in the case of horizontal, when you go top down, it will determine that change. If you go bottom up, it won't. So we can simply fix this. We have two vertical filters. V1 is the same as the one above. Now V2, we want to determine the trailing edges as well. So we just flip that filter on its axis, right? Then again, same operations, convolutions with both the filters. And now you see, you have detected all the possible horizontal edges. So the first filter is determining the leading edges, the second filter is determining the trailing edges. And then you have your all the horizontal edges are now being detected. You can do the same thing for the vertical edges as well. It should be vertical, not horizontal. Okay, now it's all good. As a concept, edge detection is feeling to be like something useful. So let's see where it can be used. So we start with a very simple problem. I have an image of a coin and I want to detect basically where those coins are in the image. So OpenCV basically provides us with the ability to do that. Now it's important to understand how this is happening, so because there is some caveat to it. So again, first thing we do, we load the image of the coin. Then we convert that image to grayscale for obvious reasons. So edge detection can be done in color as well, but it is almost always done on grayscale because what you are looking for is change in intensity. You don't bother with the color of the image, right? Then there is a second step here, which is actually very important. So what we have done is that we have blurred the image, right? Can anyone tell me why blurring is necessary? Why should we blur the image? Why should we proceed without? Why can't we proceed without blurring the image? Does anyone want to think about this? Yes. Okay, that's one point. Exactly. Yeah. So that's exactly the point that I was looking for. Let's look at the cat image again. Now, if you look at this cat image, and this is not the perfect example, but bear with me. This cat here, can you not see the mouse? Let's see if I can use this. Can you see the laser pointer? Okay. So, if you look at the cat here, in the actual image, this region and you can't see on this projector screen, but I can see it here. So these ears are actually pinkish, they are not completely black. Right? You may not, as I said, it's not clearly visible, but this section of the ear, this ear is a little pinkish in nature, it's not completely black. But the fur is black, right? When I convert this to RGB, what you will see is that here you will get some, it won't be completely black, it would have some intensity. So this would create an edge here. I don't really want this to be an edge, I want to ignore it. So when I blur it, what happens is everything turns to black, right? Because when you're blurring, what you're doing is you're taking neighboring pixels. Let's say I took this group of pixels, I took the average intensity value of those, and then to every pixel I would assign uh, that same value. So that is how blurring takes place. Uh, does anyone want to understand blurring deeply? I think we can talk about it later. It's unnecessary. Okay, so you do blurring, and then you go through this algorithm which is called U circle determination. Now, this is like a lecture of its own, but I'll go through it very quickly. What you do is that you start by blurring your image, then you use an edge detector, like I just explained how to do edges. There's a detector called the Cami edge detector. It will use that edge detector and it will detect all the edges in the image. Then what it will do is that it will assume that there are already circles present in the image, and it will iteratively try to match those circles with your edges, right? So it takes an assumption that for a circle you need 5 points. First point is the center of the circle, and then you need 2 points which are diametrically opposite to each other. So to try to create circles of different shapes, it's basically a for loop. So you start with a smaller circle, see if it fits somewhere, then you start with a broader circle. So you keep increasing its size. If you see these two parameters here, minimum radius and maximum radius, so this basically tells you how many different circles you want to test against the image. So again, it's basically like you take a small circle, you run it over the image, and you try to find whether it matches with any of your detected edges or not. And based on that, you get the final output. So you can see. So here it has plotted the boundary of the circle, and if you look at this small rhombus in the middle, it's the center of that circle. Now again, this is not very accurate because the boundary is a little shifted from the actual boundary. So that's more of a processing issue, but you get the general idea, right? This is one of the very straightforward use cases of edge detection, determining basic shapes. Okay? So now you know how to teach a child how to identify shapes. I'm sorry, a computer, not a child. Okay. So now let's determining edges is fine, but now let's try to do something a little more advanced. Now, edge is one of the most basic features in an image because in any image, even if I take an image of this room, you will see that there will be a lot of changes in the intensity gradient all throughout that image. So edge is a very small feature. You have other features like corners, right? In a corner, you would basically have, it would be like a two-dimensional feature where one of the corners of that matrix would either be black or white, and then everything else would be of the opposite intensity. Now, there are many such features which can represent different properties in the image. One of those cases where different features are being used is called face detection. You must all know what face detection is. So, what I want to do is, I want to take this original image and I want to detect a face. By the way, can you tell me who this is? It's actually Bill Gates. So, when he founded Microsoft, he went to jail once. Not because of founding Microsoft, but he was actually driving at a very high speed and he crashed. Yes. Okay. So there are a set of features which people have worked on and determined these features and these are called har features. So what har features do is that they basically try to capture different places on the face. So for example, you can see that this is a feature for determining a pair of eyes, right? Why? Because if you look at me, my eyes would seem darker than my nose, right? Because of course there's a curvature here, so the light completely, my face is not flat, right? So light does not fall equivalently on all the places on my face. So if I extract a feature like this, that means this part of the image probably contains eyes, right? Similarly, when you look at my face from left to right, you will see eye, nose, eye, right? Again, the gradient of my face is such that the eye will fall first on my face, so this place would be dark, on my nose, sorry, so this place would be darker and my eyes would be, this place would be brighter and my eyes would be darker. Okay, so again, so there are around 13 such features that are being calculated. If you know about this algorithm called Viola-Jones algorithm, which was I guess the paper was out in 2001. So that was the first breakthrough in face detection. So what they do is that they use these features, and using these features, you basically try to determine where the face is in the image. So let's look at that. Okay, so let's talk about face detection. So first, now these features are stored in an XML format. So it's basically the preview filter that we saw, which was a three-dimensional array. These features are basically just arrays, and you take these arrays and then you convolve them over the image. So we read the feature file, we read the input image, we create a cascade classifier. A cascade classifier is basically like you take that, you do convolutions on top of it, and you try to identify where these parts are in the image, right? So again, same kind of pre-processing, read the file, convert it to grayscale, detect all the features which are based in that cascade file, and then you would get rectangles out of these. So again, there is also one more thing here. If you remember the U circle example, what I told you is that you basically create circles of different sizes and then you go over the entire image to determine where circle is. But in this case, what happens is all these features actually have to appear in a certain order, right? Like eye has to appear next to eye, nose has to appear below eye, lips have to appear below nose, right? So it would take this set of features in this order and then start scanning over the image, right? So then you get a rectangle as an output, and once you draw that rectangle on top of your image, you get something like this, right? So this is how face detection works. Now let's get back. Okay, so just to give a very quick summary, we started by this idea of what humans see, how humans perceive the world. Then we talked about how we can make computers see things. So first of all, to get them to see things, we need to understand how they look at images. So we introduced three different types of images. Right? Once we know what images were, we started with a very simple problem, that is determining simple shapes. To determine shapes, we need edges. Now, to need edges, we need to find it in the image. So, how to find things in an image? We introduced that concept by using filters and then through convolution. In the convolution part, we looked at a very simple filter first, the preview filter, which can be used to determine simple edges, both horizontal and vertical. Then we talked about determining more complex features from the image, such as eyes, nose, lips, ears, and we combined that to do face detection. Now, everything that we have done until now, it has certain steps. And one step of it is to manually determine that that filter that will run on the image and tell me what I need to, what I want, right? That process is actually very complex, right? to manually understand. Okay, so let me take an example from here. Can you look at that plant? This one, right? And okay, there's only one plant. And can you look at this trophy? Right. What is the difference between this trophy and this plant? Yes. Some of you are looking at me like, what kind of an idiotic question is this? But that is actually the point when you start talking about features, is that the features of this trophy would be completely different from the features of that of this plant, right? So a plant would, so if you look, it has leaves in a particular pattern, right? Downward flowing, and I guess it's a bunch of 4 leaves that come out at once. The trophy has these markings on it, right? So in order to describe the trophy, I would need a completely different set of features. In order to determine a plant, I would need a completely different set of features. If the species of this plant changes, then I would need another different set of features, right? So manually calculating all these features is practically impossible, and sometimes you can't even come up with features. So I could have also simply explained this problem by looking at these images of 3, which I made. So if you look at this, these are handwritten images of the number 3. In each of the case, 3 is represented differently, right? And let's say for a minute, we can maybe come up with a manual feature for determining 3. Let's say I need a top edge, I need an edge here, then I need an edge in the bottom, then I need a vertical edge here, a vertical edge here, maybe a vertical edge here, here, and here, right? But not everyone writes 3. For example, in this one, you may not get this top edge at all, right? Or you may not get this vertical edge at all. Here you might get more than one edge, right? So that algorithm starts to fail. So for that, some people decided, well, there is this thing called a neural network which can automatically learn things. Why don't we use a neural network and ask it to learn features? So when I say learn features, basically instead of coming up with these matrices, these filters yourself, why not let a neural network decide what values should be within those matrices? So I will not go into detail of this because it's sort of a completely different topic. And I think we already covered CNNs once. So you basically have an input image, then you have some layers which would try to understand what the values for these features or what the values for these filters should be, what those matrices should be. And based on the feedback from the output, so basically this is a forward pass. So in the forward pass, you would just have features which are random, right? So I will have random matrices which are extracting some value from this image. And then in the backward pass, when we are getting feedback or doing backprop, that is when these weights get adjusted and you basically learn features. So this is currently, or I would say this is the most breakthrough innovation in the field of computer vision. The reason is because for a very long time people were manually determining those features, and that the use for those features would basically go away once you have variability in your data set. You have data sets like CFAR10, right, where you have images of completely different things. You have animals, you have humans, you have objects in that. You can never come up with features that can extract values for each of those, right? But you can always learn them. So this is sort of the end of our discussion, and this is how computers basically look at images and try to understand values from them. So if you have any questions, please Google. Now you can also use ChatGPT. If you, okay, I'm joking. If you have any questions, you can ask me. If you need any questions, if you have any questions or you need clarifications on anything. Yeah. Did you guys find that, were you able to understand this flow of not knowing what an image is and then how does the computer look at it? Okay. Alright, so
deep. It was quite energetic as well, the session. Right? So whatever time I spent over there, I found it really great. A big round of applause for both the speakers. Please.